Good day everyone, this is Vlad Kustov from Novosibirsk, Russia. Now I tell you about my developed theory that I named Covariant tensor machine. It is worthwhile to consider construction of covariant tensor machine. Let I have the basic data of point with coordinate in B. The trajectory of moving is circle xt. It's the fixed track and xt is the geodetic line. The start tangent velocity vector has invariant parameterized by time equal 1. The goal: search the graphical connection between the tangent velocity vector and centripetal acceleration vector. What is the line to connect the velocity and acceleration vectors? What is the invariant of the centripetal acceleration? From the beginning, it necessary establishes the polar system coordinate, where the start of coordinate O agree with center of curvature xt. After that, to define metrical tensor of polar coordinate, and the velocity is represented in contravariant component. It's the radial and angle velocities. In this place, necessary to say that the radial velocity vector defines the degree of deviation from curvature. As known, the modulus of centripetal acceleration is defined by formula when points is moving on circle. Here, in the same way, the velocity vector is represented in contravariant component. After that, it is transformed in additive sum of accelerations. There are the radial and transversal accelerations. When the points are moving, then to arise Frenet-Serret TN frame. This basis consists of tangent space and normal space. The velocity vector lives in tangent space, and the acceleration vector lives in normal space. The circle has the constant curvature. Differentiate graphically the radial velocity vector along line xt. The modulus of radial velocity depends of distance c according to the definition. The direction is always collinear basis vector of polar coordinate. It's according with the representing in contravariant component. The circumscribe in that way vector of radial velocity is itself covariant derivative. However, the derivative of scalar function is the tangent axis in point. This tangent axis goes to the normal axis of Tn frame. This event is the reflection. Every vector has the start and the end point. Then the derivative axes are two lines. Start point, first line, end point, second line. The crossing points defined the invariant of radial component of acceleration. 1 point, 2 point, radial component of acceleration. As was shown in the previous example, the acceleration vector is covector. Therefore, the remaining distance is the invariant of transversal component of acceleration. However, it discloses the new commutators. The first commutator is between the radial velocity and the radial acceleration component. Its axis to connect arrow the radial velocity with the start of the radial acceleration vector. The first commutator I call the radial commutator. The second commutator is between the start of radial vector and the arrow of radial component. Also is the start of transversal acceleration vector component. Its axis to connect the start of radial velocity with the start of the transversal acceleration vector. Examine closely the diagram of commutators. It's closed a trapezium where the line of commutators are parallel. In every moment, the projection of radial component of acceleration is the equal of radial component of velocity. Projection. Therefore, action on radial velocity involves its nulling. This event brings the absence of action from the radial commutator. The residuary transversal commutator is the future velocity, direction, and invariant. The C is the point of transformation. In other words, necessary to give length of transversal commutator and move it to point C. Transversal commutator and move it to point C. This is the operator saves the direction and invariant, then to be the new velocity vector. Mathematically, this event has been written as the action of scalar function. It follows because the Frenet-Serret TN frame is to exist on the moving off point. It can replace the action of operator on the vector to scalar function. A few words about how the covariant tensor machine works in the graphical method. In point B, necessary draw the velocity vector at a scale. But remember that action covariant tensor machine occurs in t equal 1. Then connect the end of arrow with center O. Therefore, the point of across with xt line occurs in point C. This is the radial coordinate of the moving, the same way as its angle coordinate. Xt is the circle. The vector of radial velocity is defined as distance between point C and the arrow of vector velocity. In this place, I have been given the contravariant component of the velocity vector. Contravariant component velocity vector. Now, necessary, draw the tangent lines from the end of the radial velocity vector. First line, second line. They goes to normal axis of the Frenet-Serret TN frame. The points of a cross exactly defines the vector of centripetal acceleration. Its line in scale. Then necessary, give the length of transversal commutator and move it on point C with the safe of direction. Transversal commutator, safe, its new velocity vector. That it was drawn in picture is one cycle of covariant tensor machine. One cycle of covariant tensor machine. Now I can give the determination of covariant tensor machine. The covariant tensor machine is the graphical and analytical method that to define the connection between the tangent velocity vector and the centripetal acceleration vector. CTM is the abbreviation name. Running a few steps forward, I can tell that the theory of covariant tensor machine builds on three fundamental quadratic forms. The first fundamental quadratic form is bilinear form on vectors. In other words, it's metrical tensor. This form shows how the velocity in every point depends on parameterization. The second fundamental form defines the degree of external interaction, and it tells how a curvature to change from point to point. The third form is connective, the first and the second fundamental forms. In other words, this is the angle between the commutators and the vector of velocity. The same way as the CTM defines the meaning of Weingarten operator. It's invariant of surface. Using CTM, I can solve physical problem. The covariant tensor machine exists in space of more dimensions, the same way as the CTM exists in pseudo-Euclidean space. In this case, the CTM demands a modernization. I will show you how the CTM is connected with causality principle.